Resume. So, from the morning class, we arrived at our first differential equation model for a simple epidemic, which has susceptibles, infectious, and recovered individuals. Okay? So let me write down again this model. So the time derivative, time variation of the susceptibles is minus beta s times I divided by n. di dt is the same expression with opposite sign, minus, I used gamma, yes? Gamma I, and dr dt is equal to gamma I. So, nice system of equations. So, now you have seen with Renato the solutions numerically obtained by Euler's method or whatever method you wanted. Okay? So these are the curves that are here. Okay? Just an aside commentary. There is no such thing as analytical solution to SIR model. So what is analytical solution? Okay? It's an expression that would give you S, I, and R equal to something. Okay? That depends only on time. Okay? So this is not known, but please don't make a confusion. The non-existence of an analytical solution does not have anything to do with the existence of solutions. The solutions exist. We even have a plot of them. Okay? We just can't write them in terms of known functions. Right? So it is, but it perfectly exists, the solution. Okay? So if you look at that, you see what happens. This is not a very good plot. Renato's was much better, actually, because this one seems that the susceptibles go to 0, but they don't go to 0, actually. Okay? They go to a final value, and we will discuss this. But you see that there's a curve with a peak on the dotted line, which is the number of infected people. Okay? So, now, this is the easy part. Okay? Let us now try to, from the SIR model, try to build more insights into an epidemic. So one important thing is here, this one, and the one that Renato has shown here, are always situations where you introduce an infectious person and it generates an epidemic, or a very small proportion of people. Because in real life, it's not like that. In real life, you have several introductions. It's not one person. It can be one, but sometimes what happens is just that one, for some random reason, doesn't infect anybody. Okay, even if it is infectious, but well, because maybe he stays at home and lives alone. Okay, so but mathematically, we'll say that we introduce a very small number of infectious persons, and we generate an epidemic. But it's not always true. There are situations where you introduce a small number of people, infectious, and it does not generate an epidemic. It's not always epidemics. Okay? So the question is, can I, from this model here, derive the conditions upon the parameters? Parameters are beta, gamma, and n, okay? Such that I can predict there will be an epidemic or there will not be an epidemic, okay? In this mathematical sense, okay? As I told you, in real life, you have situations where sometimes you need more than one introduction. But this is obviously not taken into account here. So in order to know this, we have first to write down what we mean by an epidemic. And what we mean here is epidemic is at time 0, at the time of the introduction of the first infectious individuals, we will have GI dt positive, meaning that the number of infectious persons increases. Right? So if the number of infectious persons increases, then you say you have an epidemic. We are not talking about the size of the epidemic, nothing, but we're just to say we have one. And if GI dt is negative, then you don't have. And this is easy to analyze. Okay? It's easy because we just have to look at GI dt, and we know that this is beta Si over n minus gamma I. But I am considering the case of a totally susceptible population where some individuals are being introduced. Okay? So then S is approximately equal to n. Okay? Because everybody is susceptible. Therefore, this is an n, and therefore this cancels. And then what is this? This is just I times beta minus gamma. And this is positive if beta is bigger than gamma. Very easy. Okay? So beta bigger than gamma means I have an epidemic. But the same thing can be put like beta over gamma bigger than 1. And this object here is beta over gamma is defined as the intrinsic reproductive number of this epidemic. Okay? It's called R. This can be, we can use R0 or R0. I prefer R0, but many people say R0. So, so if R0 I'm putting 2 bars here for you not to confuse this guy, which is a pure number, with the R from the recovered. Okay? It's completely has nothing to do with it. It's bigger than 1, we have an epidemic. And obviously, if R is smaller than 1, we don't have an epidemic. Okay? Then every course, people ask, and what if R0 is equal to 1? And then this is a non-generic case, which we don't want to study. Why? Because your equal to 1 is infinite precision equal to 1. Okay? So this doesn't exist. It's close to 1. But it can be close positive or close negative. Okay? So we won't study this. If it's equal to 1, the identity is 0. Okay? But it's always either positive or negative. So why? I forgot the 0 here. Why I'm talking about that? Well, first of all, and because this solves a problem to determine if an epidemic will occur or not in this population. Okay? And interesting enough, it does not depend on n. Okay? And this is because we have that discussion in the morning that we have put this n here. Otherwise, it would depend on n. Okay? So, okay. Now, it is a fact that we will see other models here. Okay? And you will be working with completely different models starting tomorrow in your projects. But you can always ask the question, I have a totally susceptible population. If I introduce a small number of infectives, will I have an epidemic or not? And it will turn out that that will be also possible to define, in terms of the parameters of your model, some object called R0 for that other model, which has the same properties. Bigger than one epidemic, smaller than one non-epidemic. Okay? So this is here, is the first appearance of R0, but this concept is actually central to epidemic modeling. Okay? And many of you may be heard during the COVID epidemic of people discussion R0 at the television, including me actually. We was interviewed, what is R0? So this is our friend here. Now, okay. Now, let's go back to what Renato was saying about the numerical integration of the differential equations. Numerical means I have to give here the number n, gamma, beta, and the initial values of s, of I, and of r. Okay? So I have to do, in order to, because numerics means exactly that I have a number, not a symbol there. Okay? Now you would say, okay, but I would like, therefore, to know the parameters from, can I use my data, for instance, of something I'm observing to calculate the parameters, which should be nice. Because if you do this at the beginning of an epidemic, then you could say, maybe I can predict the end, or I can know things about the future. Things are much more difficult, but in principle, that's one point. So, and if you are really near the very beginning of the epidemic in a totally susceptible population, then we can go back to this equation here. Okay? And, or this one already with s equal to n. Then you have di dt is equal to, okay, it's written here already. It's I times beta minus gamma, but I can also write this in terms of, if you want, this is gamma, divide everything by gamma, and multiply is the same thing as I multiplied by R0, beta over gamma minus 1, and I. Okay? So we know the solution to this. The solution of I of t for t close to 0, so the initial growth phase will be there will be an initial number of infectious people. Then e to gamma R0 minus 1 time. So that's the initial phase. And the initial phase is exponential growth. So, now, could I use, say I have data. And this is data for, it's not like a new emergent disease, like COVID and so on. And then you have I, then you have T, and then you see an initial surge. Okay? Well, then you can say, okay, this goes with E to some lambda, and then you can find the lambda that fits your data points. Okay? And if you find this lambda, then you have found the gamma R0 minus 1. That's what you have found. That's that you can find. So, but my parameters, N is usually known. It's the population at risk in a certain place. And gamma, you have a good idea. Gamma is the duration of the disease. And so the only thing I don't know here is beta, which is the same as I don't know R0. Okay? Because if I know gamma and R0, I can know beta. So this is a way that you could use to calculate R0. Okay? And this gives you a parameterization of your equations. You get the numerical values for your population. So this is the simple way of understanding that I can get R0 from my epidemic curve. Okay? I will today I will still show you the importance of R0, because obviously one thing is the bigger R0, the steeper is the beginning. It means that you are increasing very fast. And if R0 is close to 1, let's say 1.1, this is a small number, this curve will be like this. So you increase. So now, very nice. But there are problems. So I want you to make a critique of this. What are some assumptions that I'm implicitly making that would be a problem? So, creativity. Yes, that's true. We will see in the next class, we can adapt the R0 to something which will be called R of T, which will be the correspondent case where part of the population is immune. Okay? But okay, but let's say this is like COVID. COVID it's really like this at the beginning. You introduce a small number of people and you get an epidemic. So again, would this work well? What are the difficulties with this? Okay, but this we can have a new model, which I will speak very briefly, a carrier state, or it's a latent state, and there's also carrier states. Carrier states is when you recover, but you still are infectious for some time. Okay, so you are carrier, but you don't. And latent is you have been infected and you are infectious, but you are not infectious, because you need a certain, if it's a virus, you need a certain viral load to develop in your body until you get infectious, although you are being infected before. Okay, but this is a critique of SIR model. I want a critique of my method. Yes? Yeah. There can be, that's true. That depends a little bit on what we call the initial, because if initial is a month or two, then that is probably already okay for the deterministic. But at the very beginning, if you look at COVID in Brazil, there have been multiple introductions from travelers. And we don't know exactly which one actually ignited the thing, but it can happen, as I thought, by completely random process that a person doesn't infect anybody or just infects one person, that the other person doesn't produce a chain of infections. So, well, then you have a stochastic burnout. Okay? So it is, but okay, this is true, but if you have a long enough time, and then that would be nice. Yeah. No, R0 is a number. No. No. So we will do this in the next class. We can define a new concept, which is a kind of dynamic R0. Because you could say, that, no, but I'm not at the beginning. Okay? Is there something similar to R0? Yeah, there will be something, but we have to look exactly at the meaning. Here, for the time being, R0 is the condition for the existence of the epidemic in a totally susceptible population. And it gives you the initial growth. So let me ask you another question. What can we measure? Can I measure S, I, and R? Problem. So that is the first thing. You don't have neither S, neither I, neither R over time. You don't have any of them. Yes, prevalence and incidence. So, but it is not a problem for this method. If you look, what is the thing you get usually is the number of new cases per day. Okay? So, and number of new cases per day is the number of susceptibles that have turned on a day to infectious. Therefore, it's just this. It's beta S times I times N. But this, when S is near N, it is very slowly varying. Then this is proportional to E to I. And I has this exponential here. So this also has an I at the very beginning. It also has an exponential growth with the same rate of growth as I. This is valid only at the beginning. Well, we'll see in another moment that the curves of incidence and prevalence are not the same, although they look alike. But they have peaks, and the peaks are not at the same point. But at least for the beginning, that's okay. So then there's another new problem. This is more tricky. When is time equal to 0? So you don't know. Depends if you have a really, really simple epidemic that susceptibles get infected immediately as they get infected, they do not have any latent period. They are not exposed and then infected. Okay, that's part of our assumption. So, but anyhow, you don't know exactly when the first event of infection happened. You cannot know. Okay, So this is a problem, because, I mean, the epidemiologist's life would be much easier if it knew when the epidemics is starting. It's starting now. Bah! Take your public health measures, and I can avoid everything. But the point is that you don't know the time equal to 0. Okay? So as a method to calculate R0, this is nice conceptually. It also is depending on the model, that this model be correct. I think in one of our last classes, I will show you that it's possible to calculate R0 without model. And this will be nice. And this is state of art of calculation. Okay? It is based on something which is called renewal equation. Okay? Okay, but this is not the topic I'm right now. Our topic right now is, okay, in principle, at least in this, the theoretical setting is such that R0 can be determined from the curves of cases. Okay? So, now, could we have some better understanding of R0? In order to have a better understanding of R0, I will ask my first question, that is, given an individual, he is infectious, how many other people will he infect, on average, at the beginning? Okay? So, on what should depend the number of new secondary cases given a primary case in a practically totally susceptible population? On what does it depend? On what parameter? On what is this dependent? Rate of encounters. Yeah, infectious period. Yeah, the time. So if I stay infectious for 10 days, I can infect more people than if I stay infectious for 5 days. It should be proportional to that. And it also has to do with the number of encounters. But remember, we discussed the number of encounters times some concept, which is a more biological thing, that it's the capacity of the virus to infect you, or the pathogen to infect you. Okay? But this was beta. Okay? So the number of secondary cases should be something which is beta times the duration of the infectious period. Okay? Which is 1 over gamma. Which is, hurrah, R0. So R0, mathematically, it came out of the condition to have an epidemic. Or putting this in mathematical jargon, this is the condition for the disease-free equilibrium to be unstable. Okay? And, but it turns out that this same guy is the number of secondary cases given a primary case in a totally susceptible population. So this gives you a more beautiful interpretation, and one that is also easier to grasp if you're not a mathematician. Okay? So, nice. Then you could say, okay, then I can have a new way of calculating R0. I look and I want to know the secondary cases given a primary case, but this is not possible in general, because you have to have the chain of infections of several individuals and then get a kind of average number of people that have been infected. But I mean, you don't do this as an experiment. You cannot do it. You are infecting people. Okay, it's not allowed. But well, you could have something like we had at the very beginning of COVID-19, which was in China. There had been a lot of household transmissions. Okay? And you could reconstruct the chain of infections for secondary, tertiary, maybe 4. So you could get it for a very limited data set. But then you could already know that, for instance, it's not 10 R0 for COVID. Okay? But it also is not like 1.1. So you could have a kind of estimate of the range. Okay?
There's also a nice point about R0 that once you define it like that, it's independent of the model.
Yeah, that's true. It's independent of the model. Okay? That once I write it this way, I mean, not this here. R0 is the number of secondary cases and so on. Then it doesn't depend on SI model. So it is a concept that can be defined for any epidemic. Okay? So for COVID, we had a range of, I think, between 2 and 4 from the initial data of COVID, which turns out to be important, and I will discuss this a little bit later. Now, yeah. No, well, you would have a different condition. Yeah, a different. The thing here is strictly connected to this, but this other definition of secondary case coming from a primary case is not dependent if the person will die or not later. Okay, so any variation of this model will give you a new expression for R0 in terms of the parameter of the model. Different models have different expressions for R0. But still, it will be true that this guy here, the correspondence will be true. And this is the beautiful thing. It's something that is very epidemiological. It's secondary cases, and it's related to a mathematical concept like that. Yeah. That's a beautiful thing. Now, so if you have a big R0, you are in trouble, yes? So today is the day of lists. Let's just list R0 for some diseases. Now, there is a comment before that. R0 depends on the disease largely, but also may depend on which is the population that you are studying. Okay? But, okay, so measles, our model disease. Measles, it's about 18. This is one of the highest ones that you can get. The competitor to this is pertussis, which is also very high. Now, so you could go for smallpox, which doesn't exist anymore, but you can go for historical data, and it's about 6. And polio is about 7. COVID at initial phase for the wild strain, not for the variants. It's 2.5. All of this is more or less, okay? It's not exact numbers. No? And Mpox, it's about 2. So what else? So dengue So dengue, it is a more tricky because it's a vector-borne disease. So, but you can think I am here, and then through the chain of infections using the mosquito and so on. Well, how many people will be affected at the end? Okay, so you can think of this, and dengue is like 1.5. And other diseases like cholera, for instance. So cholera is very dependent. How you get cholera? Cholera, you get you have the bacteria. So it's the Vibrio cholerae that goes into the environment in the water, and this will be in touch with people. They will actually eat it or drink it directly, or because the water was used to wash something. So it's very dependent on the condition, sanitation conditions. So cholera depends pretty much on the social environment. But there are numbers for cholera, which was calculated in Tanzania. And it was approximately 2.7. Ebola, which is scary, but Ebola has a small and well, the other ones I have here is a syphilis, calculated for Japan, because this has also social component, okay? If it's a sexually transmitted disease, it depends on the sexual culture that you have studying, was 1.3. And actually, I should have discussed it longer this, because this depends on the climate, okay? So actually, this value is for temperate climates, but it can be like in tropical environments and subtropical environments, like 3.5. So you see, that's dependent on climate in this case. So now this gives you an idea and about the values that we are talking about, and we will try. I will try to show you maybe today that R0 can be very important for knowing what Renato already talked, the total size of the epidemic. When the epidemic burns out, if it burns out, but if, say it burns out, it goes to 0, the number of infected people, what is the number of people that have been infected over the course of the whole epidemic? That's the total size of the epidemic, and I will show you that it depends only on R0, okay? Which is nice. Why it's nice? It's calculated at the beginning and gives you the total number. But there are problems with this also, but let's first proceed. So now, Renato also taught you about with the phase space. Okay, so this would be a diagram. If I put S here and I here, and then look at the trajectories, S and R. S and I are time variables over the time, you will have a curve here. So you can find this, and this you can do much better than finding the solutions. In order to find that things, you have to do a mathematical trick, which is take this equation here, which I will call equation 2, and I will call this equation 1. Just another thing. R is not present here. So this is effectively only 2 equations that you have to obtain. So you divide 2 by 1. You divide one equation by the other. Very, very ugly procedure. But this gives you GI, GS, because you will have this divided by this, and you still cancel the dt. Ah, horror scenes. Children out of the room. So, and this will give you have the beta Si divided by n divided by what is above, which is minus, I would put a minus here, beta Si over n. So this is 1, okay? Yeah, this is 1, because this is minus 1, sure. And then you have the next term, which is minus gamma I divided by beta Si over n. Okay? So all of this will result minus, yeah, minus plus. That will result in I being equal in GIDS being equal to minus 1 minus plus this. And I cancels here. You will get gamma over beta, which turns out to be the inverse of this, 1 over R0. S and N. Okay? Guess what? Yeah, that's it. And you see, there's no gamma and beta independently. It's only R0 that appears. Okay? And now this is DIDS is equal to some function of S, and I can make this, solve this, integrate. I can find I in terms of S, not in terms of T. So that will give you I, will be the integral of this, will give you minus S plus N divided by R0 times logarithm of S. And you are happy. But there, sorry, plus a constant, okay? So we have integrated this. So now you need to say the value of k. You have to use the initial condition. You say at the beginning, I will have I of time 0. I will put it 0 or approximately 0, okay? And S of time 0, the population is totally susceptible, gives you equal to n. In order to be satisfy this, then you have here that I of 0 is 0 equal to minus S, which is minus n, plus n over R0, logarithm of S at time 0, which is n. Okay? So you solved it. You put this here, and you get the final expression. Okay? Which can be written like this. It is n minus S plus n over R0 logarithm of S divided by n. Now, in order to make the plot more convenient, I divide everything, both sides, by n, so that I have now the fractions 1 minus S over n logarithm of R0 S over n. So this I over n is the fraction of infected people, and S over n is the fraction of susceptible people. And now this is a plot of I in terms of S. What? Ah, yeah, sure. Sorry. Okay. And that's the way to calculate the constant. Okay, sorry. So, then you can do this. It's not so nice to calculate, to plot a 1 minus logarithm. It's not very difficult, okay? So, here, you will always start. Let us put S over N and I over N, so I can get rid of N. Okay? And this will start always at 1, because we are considering that at the beginning everybody is susceptible. And this will do something like that. Different values of R0. Each curve is one curve for a precise R0, because you have to give R0 in order to make the plot. Okay? Gives you something like that. So you have the phase space, analytic calculation for the phase space. It only happens with the SIR model because it's effectively two-dimensional. But well, now, can we learn something about that? Yes, we can learn. So we can learn that at the end of the epidemic, S is not 0. When I is 0, here, this line, S has a certain value. At the end of the epidemic, there are still susceptible people. It's no epidemic will infect everybody. Although, if you put this 18 here, then you're very close to 0, okay? But for others, not. So this would be typically 2, okay? R0 equal to 2. So at the end, there are still susceptibles in the population. This is an important fact about epidemics. It's not everybody that gets infected, although everybody could be infected. Because here we are assuming that they are susceptible, but not everybody actually gets infected. So then you say, okay. Can we calculate this value of S when I is equal to 0? Can we calculate that? So it turns out we can. Okay? So let us go back to our nice equation here. This one. Okay? I forgot a plus sign here, okay? So in the end, I will put time equal to infinity, okay? Meaning the end, okay? It is never infinity, okay? But mathematically it's infinity, okay? But at the end, what I have is I is equal to 0, okay? So you have 0 equal to 1 minus S infinity over N plus logarithm of S infinity divided by N divided by R0. Okay? So this is an equation for S infinity. Then obviously that has a solution. Obvious that S infinity equal to N is also a solution of that. But we know this corresponds to time equal to 0 and not to time when at the beginning, when I is also 0 at the beginning. So that's not the good one. That we want to have that I is not equal to 0. So what we want here is is to write the following: 1 over R0 times the logarithm of S divided by N is equal to S divided by N minus 1. That comes from here. Okay? You put this here on this side, and you get this. So this is an equation for S over N. You can write this as the following. The logarithm of S over N is equal to S over N minus 1 times R0. Right? You multiply both sides by R0. And then you take the exponential. That gives you S over N is equal to exponential of R0 S divided by N minus 1. Okay? So this is an equation for S infinity. Okay? I omitted the infinity, but that was our assumption. Okay? So this is an equation, which is not a differential equation anymore. It's an equation for the number of susceptibles at the end. Now, you'd say, okay, but this is a very, very bad equation because it's a transcendental equation. Yeah. Life was too easy until now. Now, we have a transcendental equation, but no matter. You can solve this numerically, okay? And then you are okay. So, if you do this, you will obtain S infinity. So, S infinity can be obtained from this equation. Okay? And I will show you, but already Renato showed you, and give you some context. But at the end, I also have S infinity plus I infinity, this is 0, plus R infinity is equal to N. The total population is constant, and at the end, it's composed of the susceptibles and the recovered. Therefore, if I know this guy, I can know this guy. Okay? So if I know S infinity solving this equation, I can immediately calculate R infinity. Therefore, I can calculate the total size of the epidemic solving this very ugly equation. Okay? But I mean, it's something that is not difficult to do. And what happens here is that if S infinity, here this equation, S infinity over N, I mean the proportion of S infinity, depends only on R0, and not independently on gamma and beta. Okay? It depends only on R0. And if this depends only on R0, then the total size of the epidemic also depends only on R0. But this is, at least from the theoretical point of view, very beautiful. What does it mean? It doesn't mean that if I can calculate R0 at the beginning, I know the potential number of infected after the epidemic burns out. So something I calculate at t equals 0 has an implication for t equals infinity. And this is super good. That's what we love. Okay? Well, okay. So, then I will repeat here the plot that Renato did. And what happens here? Here, this one. Okay, this one. This one I don't need anymore. So this is the basic reproductive number, or ratio if you want. R0 on the x-axis, and the final the total size of the epidemic, the number of people that got infected during the whole course of the epidemic. And you see it's an increasing function. And it gets very close to 1 if R0 is over 4. Okay? Just by looking at 4, you get very close to the fraction of infected being 1. Means that practically everybody had been infected. Yeah. While if it's smaller, then let's say if it's 2, it will be about like 70% of the population. So this is this curve is a disgrace. It's a very unfortunate surface. It grows very rapidly with R0. Okay, so imagine now measles. Measles is 18. It's far beyond of this curve. Okay, so it's practically 1. So and that is also important in some practical ways, but let me tell you a piece of, can be now called history. At the very, very beginning of COVID-19 in 2020, and in the United Kingdom, UK, the Prime Minister was very bothered and did not want to take action like leave people at home and so on and so on, right? So, but you know, UK, from epidemic modeling in UK is very strong actually. But they have a very strong group at Imperial College and at the London School of Hygiene and Tropical Disease. They have very good modeling there. And there's a person that's kind of the, if there were a Nobel Prize for modeling in epidemiology, you'd win it. How is it called? Ferguson. What's the first name of Neil Ferguson? And so he made this calculation. So okay, let's see. From the China cases and so on, so you have to have what kind of R0. So put it like 2.5, 3, try a little bit between 2 and 4, and then you can calculate the total number of infected people. But COVID also kills, so it's not an SIR model. But you have a certain proportion of people that will be dead. Mortality is not 0. Then you can also calculate how many people will die. Right? And then it came out for calculated for UK and for US. And USA it would be like 2 million, and then UK would be, I can't remember now, it's like over 500,000 deaths, which made the government understand that they had to take action. Now, this has been decried because, well, first, it was very difficult to know the actual mortality of COVID because you had only the data from China and the very initial data from Italy at that point. So actually, the estimate used higher mortality than in reality, because at that time it was not clear what would be the proportion of mild cases, so either asymptomatic cases or what is called oligosymptomatic cases, but you have only some small fever, which is not very clear what kind of things you have. You just doesn't feel well during 2 or 3 days, and then you're like, okay, this is called oligosymptomatic. And so it was not known. And this obviously, all of this can modify the calculations. But at least you got an order of magnitude of the problem. Okay? That's important. You get an order of magnitude for USA 2 million. Now, when then some months later he got very criticized because we are not seeing so many deaths. But this is obviously a misunderstanding of the thing. There's one point. These guys and a whole world of people, of models, and even epidemiologists, pure epidemiologists and so on, didn't understand at that time the need to take care with your communication about things. So here was that calculation based on these ideas was made for the worst case scenario, where people don't do anything. You don't do anything, and you have a wild disease going on, and you don't take action. Then you would have, say, 2 million in UK, in US, okay, approximately. Even it's not exact number. Maybe it's just 1.5 million, but still, it's not like 100,000, and it's also not like a whole population. So, but it's a very sizable number, okay, which demands clear action in order to avoid it. And obviously, even if the government doesn't do much, people will react also. They will behave differently. So we have seen this in many situations. For instance, that people get scared, and even if the government says, I don't care, it's some governments from some people that we know actually were like that. But there are the mayors, there are governors, there are other public health officials, and then the people that are scared. I'm scared, I will stay at home. And even if the government says that you don't need to stay at home, I will stay at home, because it's a reaction to a situation, okay? So then you never have the worst case scenario, okay? So this is a self-defeating calculation, because if you say you have 2 million people can die, people will say, okay, I will better take care of myself, okay? So it's a self-defeating. But anyhow, it gives you the good, gives you an order of magnitude of the kind of problem that you can have in this situation. And that's it. It's actually very important, okay? You can refine the calculations, you can make a lot of things, okay? But it gives you the order of magnitude if you don't do anything. But as I told you, even for instance, if you don't have any enforcements, like we had the epidemic of Mpox in 2022, okay? And we will discuss Mpox in this course more at the beginning, because this involves certain aspects of modeling which are really challenging. But one thing that data shows is that the biggest majority of the cases, at least the symptomatic ones, is in men that have sex with men. So and this was initially connected to the Northern Hemisphere summer of 2022, where there's lots of raves and clubs and things going on, and the number of sexual contacts has been very big. So when the problem emerged, well, the people canceled the parties. And so that's an example of nobody tells them you are forbidden to have the party. No, but I'm not. I take care of myself. I don't go to this party. Okay, so this is an example of cases where you have the reaction from the population. This actually connects, and on Saturday I will talk to you about challenges of present-day epidemiological modeling. And this connects to a very big challenge, with a challenge that is difficult. It is write down epidemiological models that take into account behavior and behavior change. due to the epidemic. Interaction between, but behavior, it's how do I quantify behavior, and all of this will be not so easy, and actually there's still a lot of progress to be made in this area. Yeah? Okay, now, very nice, but let's go and say, look at the peak of measles in New York City. Okay, that's at the peak. Wow, nice peak. Can I now use my model, SIR model, and predict this and see if it fits the peak? Why not? Good. So you do this, you take your SIR model, you solve it numerically, you take the population of New York, like, and that time was like 7,700,000. So, and R0 is like 18. 1 over gamma duration is like 5 days. You have everything. Then you say, what will you get? Do I get something like that? Yeah, you get something like that. But you get something which, I don't think I have the plot. Let me see if I have the plot. No, I don't have the plot. You will get a nice peak, which obviously is not exactly like the peak here, but it resembles. But look at that. Monthly cases were like maximum 8,000 at the peak. Okay? And if you do the calculation in this naive way, you will get a peak with like 600,000 people at the peak. So what's wrong? What is wrong? Well, it's true, but that's not. It would not never scale to such a difference, okay, between 8,000 and 600,000. It's not the random. That could be, but measles, people actually wanted to put the kids together to have measles, so they do it only in hands. Okay, people get to the school with measles. All the class get. That was a reality 60 years ago. Unreported cases. Yeah, but there are always unreported cases. But this scale of unreported cases from 600,000 to 8,000, it would not be unreported. Sure. That's the point. Initially, S of time 0 is obviously not equal to N total population, because we have the other plot. We know that this is going on for many years. So population has immunity. Therefore, my initial population is only the population of susceptibles, but the susceptibles are not equal to N. The R, actually, the recovered guys or the immune guys, form a vast majority of the population, because measles was typically the case of childhood disease, and so pretty much everybody got it. As I told you, I myself, I'm born before the vaccine availability I got, measles. Okay? And so then you say, okay, but then I could modify my calculation. I can redo this, not assuming that S at time 0 is equal to n. I will assume something else. Okay? I can redo this calculation, including the fact that we have immune persons. But the point is, what is the size of the number of susceptibles if it's not n? What's the size? Because you have the whole history of the disease. And then you have that from one model, how can I actually calculate S0? Problematic thing, very problematic thing. Okay? Because as you say, you never measure these guys. Okay? In only very few cases you can measure some of them. And one of the cases is a high mortality, like Ebola, then you can get the R, which is not recovered as that, but anyhow, it's not participating in the pool of the epidemic. But this is a problematic, and actually, there are ways, but I will need to develop more theory to guess more or less what happens. We'll do this tomorrow. And will allow you to guess S0. Okay? And so the right value is like 6% of the population, not the whole population. And this will make a very big difference. And if you do this, you actually get something which has the same order of magnitude at least, which is nice. Okay? But we need to know the initial number of susceptibles, and this is not readily available. You have to find some way to calculate this from some other ideas. Okay? So you see, life can be difficult. As I told you, the mathematics is the easy part. Right? You just go to calculations. You need a lot of calculations, but well, when you get to real-world problems, then you have to think about actually what are the variables that are measurable, and so on, and so on, and so on. So, well, one thing, I don't want to do the calculation, although I have written it here, is just to remember that there is a difference between the curves of I and the curves of the incidence. Incidence is the number, but if you go to an epidemiology book, not of the modeling, but each book has a different definition and so on. But for us, incidence is the number of new cases per unit time. Let me make an observation practical. What is usually the time, the units of time, the length of time that we use in epidemiological studies? Because you can say, well, if you look for COVID or something, that you have new cases every day. Huh? But not all days are the same. From the epidemiological point of view, from the disease point of view, all of them are the same, more or less. But for our surveillance system, they are not. In particular, you have Sundays. And if you do the plot for COVID, we did this during COVID, for on a daily basis, you have peaks every Monday. Okay? So this is an example. And why? That usually the things that are presented in epidemiological studies are weekly reports. So weeks are very similar, although they are holidays and so on, it can spoil a thing, but it's better than days, because you have 4 problems per month. All the Mondays are problematic data. Okay? So you use weekly reports. So the incidence is a new number. For us, at this point, is the number of new cases per week. Okay? And I is the number of active infections. Okay? Some people call this the prevalence, but there's also different definitions of prevalence, which is the total number of people that have already been infected or so on. So, but just to make it clear here that I is the number of people that are infected at a certain time, and the incidence is a new number of infected people. And so, and this is what you get from reports. Okay? You don't get this. Moreover, well, there are lots of things that are difficult with that. Okay? One is that there are unreported cases. And there are asymptomatic cases for COVID, for instance. We didn't take this into account here, but for COVID, you have it. So these are, and then there's also an effect on connected to the epidemic surveillance. Is that when you have a large number of people going to the clinics and so on, reporting is very much delayed, because at least in Brazil. Why? Because who makes the reports? So typically you should have an epidemiologist at every health station or health district or whatever, but you don't have. Okay? So somebody has to do the reporting. Sometimes are the physicians, and sometimes are the nurses or other medical people, and they are overwhelmed by the fact that there are a lot of people in serious conditions. So the last thing they will do is the reporting. Therefore, the reporting comes 2 or 3 weeks after the things happened. Okay? So you will see this in the course of Marcelo Gomes. Totally explain you how to do modeling in this context, which is modeling of an ongoing epidemic. Is very different from the model for an epidemic that are already passed. But anyhow, we know that this has something like that. And there's a peak here. Okay? This one also has a similar thing. So, but let's say here, same time, this one has a peak before. The peaks are not at the same time. Right? So, again, remember with COVID, and I remember well because we had a modeling group here. It was called Observatório COVID-19 Brazil. And we got a lot of journalists calling us. Are we already at the peak? That was the question. When will the peak be? So I had learned with other people that I should never answer this question, because it probably will be wrong answer, and probably it will be wrong because usually you don't know exactly. Okay? You cannot answer it. But people also thought that when I got the peak of the incidence, I'm already going down in the number of cases. It's not true. You're still here at this time. You're still increasing, and the peaks are not at the same time. Okay? At different peaks. Okay? So you can show this mathematically. It's not very difficult, but I already did a lot of mathematics, so I will leave this for now. So now we are coming to the end, and let me just make some further comments, also out of our experience with the COVID, is that one thing that you may think, say you're a physicist and you do an experiment. Then you have your lab and you have bought some machine or something, laser machine, whatever, vacuum machine. And all people that have ever been in a lab, or even if they have not been in a lab, like the mathematicians or the theoretical physicists, know that the measurement equipment has a finite precision. And you cannot say anything below this precision. That's facts of life. No equipment is perfect, although people do very precise measurements in physics, which is not the case in epidemiology, or also for the case, also not in ecology, because you cannot manipulate your system as you want. When a physicist can, because it's not about life, it's about I don't know, atoms or whatever. Yeah? So we can think about our reporting system from the modeler's point of view as our measuring apparatus, measurement apparatus, okay? So that gives us the data, okay? But then you also have to think that this is not perfect, and it's not easy to, I mean, the analogy goes up to a certain point only, okay? But there is something that you never forget, that the reporting system is not totally precise. What would be the sources of imprecision? Well, as I told you, there are cases that are not notified. This will depend a lot on what is the disease that you are studying. For instance, at the beginning of COVID, there was a lot of pressure for notifications. But for instance, it is a well-known fact that for dengue, when you have the dengue epidemics, many cases are not reported. Because, well, it's not sometimes it's a matter of life or death, but most of the time not. And there are lots of cases. You go to a health clinic or whatever, or go to see a doctor, and he says, okay, that's dengue, and so on, and he will not report. Should he report? Yeah, should. But he has other priorities, and that's normal. Right? No, priorities are to be there for the maximum number of sick persons. So there's underreporting of dengue, it's notable. And then you had also, when COVID, at the beginning was okay, but later on, it was a real mess. Because there were many cases and so on. You had actually two reporting systems. One for the people that get hospitalized, which is called, in Portuguese, CVEP, CVEP-GIP. And the people that don't get where notification reports were on another one, which is called ISUS. And nobody ever could do any modeling with the mild cases. No way. Everything that people tried to do with that, even people that had better information than the public information, for instance, a colleague of us from the Fiocruz Foundation is a very good data analyzer and so on. His name is Osvaldo Cruz. And no way. So COVID, for instance, what you did is, let us take the cases of severe respiratory respiratory acute infections, and which are the people by definition that get hospitalized. And this is really reported. This is reported. Because you have a hospital, they have to report that. Although there are delays, but this is reported. So this is the data that was used in most of the cases for modeling of COVID, which is people hospitalized, and then you say, well, that is proportional. So the total number of cases, okay? So you say the incidence would be proportional. But for instance, if you want to calculate R0, you can use this. If this proportionality is true, at least for a certain range of time, then you are okay. You can use this. Yeah? So you see, again, mathematics is easy. Difficulty is really connecting this with, you have to know the details of what you are doing. And you have to know how the reports are done. For instance, sexually transmitted diseases. And you would like to know the number of partners that a person had over a certain time of. You go and ask people, okay, and they lie to you. They don't want to. They don't trust you. So it's a problem getting this. So data for sexually transmitted diseases are notably very difficult to obtain. So this you have to take into account when you do models also. Okay? You cannot do models for something that never will be measured. You have no connection to the world, and it's not possible. Okay? So that's it for now. We have a coffee break, and then at 4, we have a second class from Renato, which will be in the 3rd floor. There's a computation room, computational lab, which by has no computers. Once in the past there were a lot of computers, but they got old and never were replaced, so there are no computers there. But this is the computer lab anyhow. Okay, it's kind of name, honorary name for the room. Okay, so see you in half an hour.